Welcome back to Chapter 2. This video is going to take us through the last 3 sections. We're going to talk about Venn diagrams, and you're going to get a little bit of bonus math in this one. Let us begin. So for us, when we're doing Venn diagrams, the way that we're going to do it for pretty much every problem in this course is we're going to draw a big rectangle. That's going to be the universal set. And inside of that, we're going to have various circles. I think up to 3 is probably the most we're likely to see in any problem for this course, which are going to represent various sets within that universe. If a circle represents a set, then everything outside of that circle represents the set's complement. That's what we see up here. And then we can represent subsets by just drawing circles inside of other circles. So this is how we're generally going to represent or think about intersections on the left and unions on the right. And last video we finished with an unproven statement that A intersect B should be equal to the complement of A union complement of B and then the complement of that. So everything that's not included in that union of complements. And we can see that here in this Venn diagram pretty easily because this red zone in the middle is clearly A intersect B. And then if we try to locate A complement union B complement, well, A complement is everything that's outside of this green circle. And this is going to get ugly very fast. Bear with me. B complement is going to be everything outside of this blue circle. And since we're talking about the union, that means that this inside this parentheses, that describes everything that is now colored either green or blue, or both. And we see that that is exactly every place except for the red region. So we throw a complement on the end of that, and the statement is true. Okay, and we've spoken about mutually exclusive sets. That's just going to be 2 circles that don't overlap. So these 2 clearly have no intersection. Let's roll. So we've got a universe consisting of integers in between 1 and 8, and we just want to illustrate with a Venn diagram these 2 sets, A and B, within that universe. So this is when A is in little letter A. Okay, in little letter A, we have these 2 sets for A and B, and they have an intersection of 3 and 8 because we see the 3 and 8 show up in both of them, and then the other numbers are just left in the various circles where they belong. And then we've got the 7 hanging out here because 7 didn't appear in either of those 2 sets, but it was in the universe. And then we have a similar thing happening over here in little letter B, except in little letter B we see that set capital B happens to be a subset of set capital A. In fact, it's a proper subset because they're not equal to each other. So that circle is entirely contained, the B circle is entirely contained inside the A circle. And in this case, we have still a few more numbers that were just not included in either one of them. And then in letter C, we've got 2 disjoint sets as they do not share anything. Onward to section G. So this is just about problems where we're very interested in how many elements there are in various regions of the Venn diagram. So like oftentimes there's just going to be a lot of elements in these sets, and so one way to illustrate that is by using parentheses. So this doesn't mean the number 11 is in the set Q, it just means that there are 11 elements that are in set Q, but which are not in set P. There are actually 3 elements that are in set Q and are also in set P, for a grand total. Brace yourselves. There are 14 elements in set Q, and there are 10 elements in set P. So we just answered that one. That's 10. Not Q, that's going to be those 7 and those 4, so that's a grand total of 11. P or Q, That's the union. That's all three of these put together, so that's going to be 21. P but not Q is just going to be that section, so there's going to be 7 there. Q but not P, same idea. That's going to be 11, and neither P nor Q. That's our 4 that are hanging there in the corner. Down below, now we see it written down using symbolic notation, but this is all mental math. Okay, here's another one about numbers. We're in section H already. How exciting. There were no notes in section H. This is just problems. So the way that I would approach one of these, where we're told the numbers in various sets in advance, is to build the Venn diagram, but we always build from the inside out. So here's what the final product would look like. And when I say from the inside out, I mean I would start with the intersection. So I know there are 6 elements in the intersection. So I'd fill that in. Then I can say to myself, well, there's a total of 17 in B. So that's these 6 plus 11 more. That's how we get those. And then same thing for A. It's a grand total of 14. So that's the 6 in the intersection plus 8 more. And then my universe has 30 elements in it. So I just add those 3 up and I subtract from 30 to get 5 elements, which are in neither A nor B. And now we can answer these other questions. So what is the number of elements in the union of A and B? Well, that's just going to be those 3 there. So that's going to be 25. And then, yeah. And then the number of elements that are in A but not in B, expressed in words here, expressed in symbols here, in A but not in B, that's just going to be those 8, right? Same thing here. We've just got like words happening, whatever. So we have 27 members in a club. That's our universe. There's 27 members. And we're interested in their hair and eye color. Okay. So we're going to use, now black and brown both start with the letter B, so I think using BL for black hair and BR for brown eyes is great. If you wanted to use H for hair and E for eyes, that'd work just as well. Whatever. Again, now starting from the inside, we know that 11 have both black hair and brown eyes. Since 19 have black hair, that's going to leave an additional 8 in the black hair circle, and since 14 have brown eyes, that's going to leave an additional 3 in the brown eye circle, and then subtracting that union from our universe of 27 gives us 5 left over. So the grand total with black hair or brown eyes, that's our union, so that's going to be 22. And then the number with black hair but not brown eyes is going to be just that 8. Well, some problems can be a little more interesting. This one we're going to have to use some algebra because we don't know how many there are in the intersection in this problem. We know the universe has 25. We know there's 18 total in one set, and we know there's 17 total in the other set. By the way, the obvious wrong thing to do is to try to say, oh yeah, there's 18 in one circle and 17 in the other circle, and then forget that 18 plus 17 is bigger than your entire universe. So don't be dumb, okay? So the way we want to do this is with, like I said, algebra. So we'll put an x in the middle for the intersection. We don't know what that value is, but the total left over here from 10 meters, represented by the t, is 18 minus x, and then we have 17 minus x in set F, which is for 4 meters. And we have, obviously, there's no one out here externally from the 2 sets, because if you're not diving from 10 meters and you're not diving from 4 meters, then I guess you're just not on the diving squad. I don't know anything about diving. Maybe there's other heights in various competitions, but it can be inferred from this problem that there's nobody left out. So what do we know here? Well, we know that there's got to be 25 members in total right here. And you know what? If we put these 3 together, we're going to get 35 minus x is equal to 25. And so we can use that to solve for our x, which is in the middle, and that's going to be 10. So it's easy once you've got the visual there. Okay, last example from our book here. A lot going on in this one. So first of all, this is our first example with more than 2 circles. So we're going to have 1 circle for the bus, 1 circle for the train, and 1 circle for the cars. And then the other thing that's confusing about this one is that it uses percentages. So my recommendation is, for a percentage problem, just pretend that the number of elements in the universe is 100, right? Because your percents all have to add up to 100%. If your problem has decimals in their percents, then just like tag a decimal on here and carry on. Okay, so for this one, first let's define our sets and start building our picture up. So again, I think it's smart to start with x in the middle. Now, where does all this other stuff come from? Well, we see right here, 13% had caught a bus and a train. So that's our 13 minus x. And then we have 5% had been on a bus and in a car. So that's 5 minus x. And then 9% had been on a train and in a car. So that's going to be our 9 minus x. And then to fill in the final outside pieces, we know that, say, 46 had caught a bus in total. So 46, where is that 46 going to go? Well, we've got this 28. Where did that 28 come from? 46 minus 13 is going to be 33. 33 minus 5 is going to be 28. So now I've got to have a 28 there. Now why is it 28 plus x? How do we know there's going to be a plus x there? Well, if we look at this whole circle, the whole thing needs to add up to 46. And we've got a minus x and a minus x, and here's a plus x. We need another plus x there to cancel out with the other minuses so we can get a grand total of 46. And we'll do the exact same process with the other two. They both have an x plus, and then that number is just whatever left over. So we had 37 for the train. 37 minus 13 is going to be 24. 24 minus 9 is going to be 15. So that's how we got that 15. And same idea for the 17 down there with cars. And now we can actually try to answer the question. We're searching for x. We want to know the percentage of students who use all 3 modes of transport. So that's what we're looking for. We know grand total's got to be 100. So we're just going to add up everything inside of here. And it should equal, well, 89 because we have another 11 right there. So we're adding up everything, plus that 11 is equal to 100, whatever. Solving it, easy, x is equal to 2, so 2% of students use all 3. So that brings us to the bonus mathematics section of this video. Maybe you can figure out what the various sets are in this image here, and perhaps you'll learn a little bit about languages and how alphabets have developed throughout history by thinking this over. Now that's another example with 3 sets. And we didn't see any with 4. Like I said, in this course we'll really stop at 3. And really, 3 is where Venn diagrams mostly end, at least in 2-dimensional representation like what we're doing. Here's an example of a 5-set Venn diagram, but you can see that they get really complicated really fast. And the more sets that we have, the more regions that we end up having to show. And there's a pretty obvious pattern there with powers of 2, right? So the number of regions grows very fast. And what makes a Venn diagram special, and this was not stated earlier, is that a Venn diagram must show every possible region. So even if, in this case, we've got 31 regions here, even if some of them happen to be empty, which will be pretty likely when we start having lots of sets, right? we still need to show them if it's to be a true Venn diagram. But oftentimes in real life, there's going to be empty regions. And we can still represent things with something similar to a Venn diagram that includes empty regions, and that is called an Euler diagram. So here's some examples of those. Here's one about the British Isles. And certainly it makes perfect sense that the oval representing Scotland does not intersect with the oval representing England, because there's no land that's both Scotland and England, whereas the oval for Ireland does intersect with the oval for the United Kingdom, because there is some land that is both Ireland and the United Kingdom. Specifically, that's Northern Ireland. But we see that there are many empty regions here, and they're just not included in the image. So that's an Euler diagram. And here's just a couple more, also having to do with geography. So here's the Kingdom of the Netherlands. And here's the EU and other associated things happening over there. All right, so Euler diagrams actually much more, I think, useful than Venn diagrams, but they just don't get the love. No one knows what an Euler diagram is. But now you do. So good for you. So here's a little challenge. We're going to draw all the possible Euler diagrams that have two sets. All right, maybe you want to pause and try to do this on your own. So here we go. One way to draw an Euler diagram with two sets is, just like a Venn diagram, to draw two sets overlapping. Another way is to draw one set and a subset inside of it. And green being on the outside is the same as blue being on the outside for the purposes of this illustration. The third option, they could be just joint. Fourth option, they could be actually the exact same set. Close enough. And the fifth option, I've already drawn it. The fifth option is that both sets are actually empty sets. And so we'd represent that as an Euler diagram by leaving it blank. But in any of these cases, if I wanted to draw a Venn diagram, there's only one way that I could do it, and that's this way here. I would just make a note in my Venn diagram. If it were this one down here, if it was situation 4, then this would be empty and this would be empty. Everything would be in the intersection. If it were Venn diagram number 3, where they're disjoint, well then actually this part would be the empty set, because there would be no intersection. If it was Euler diagram number 2, then, well, if blue is entirely a subset of green, then I guess just this part would be empty. But then I would have elements in the intersection and within the green circle. And of course, if it were Euler diagram number 5, then I would just note that all 3 of these were empty. So we see Euler diagrams have a little more versatility. We can represent different situations more easily and I think more intuitively than we can with a Venn diagram. And if you get everything that I'm saying here, and if you're a fan of Christopher Nolan's films, then this is hilarious, I assure you. Let's finish this off now with a very quick quotation from Albert Einstein, very famous, smart guy. I'm sure you've heard of him. Well, he once said, "I have no special talents. I am only passionately curious." And so I encourage you to be as curious as possible in all areas of your life. Follow that curiosity wherever it may lead, and let that help you to develop whatever talents you may have as well.